Okay, so we're going to start with a polygraph, Desmos. We've done these before, and I hope you remember. This is the game where you're paired up with someone. One of you, both of you see the same 16 graphs, and then one person hides one of them, and the other person guesses by asking questions which graph the partner is hiding. So I hope you remember that. If you don't remember, when you come in the activity, there's a little mini practice session where you play against the computer. But I think you will remember, and if you don't remember, get to the practice session as quickly as you can, and then you will be able to play, which is going to be a lot of fun. And then we're going to talk about it a little bit. Then we're going to do a little bit, well, kind of what we did last week, last class. We did the anatomy of a rational function graphically. What we're going to do now, oh, there's James, good. What we're going to do this time is we're going to connect that graphical representation with the algebraic form. So we're going to do a little Jamboard that is going to look similar to what you did last time. And then that will solidify these notions and bring them together. Then we're going to talk about the next Desmos assignment, and we're going to talk about also about the rest of the course, because we only literally have the month of May and maybe 1, maybe 2 days in June, because it's night school. So that's kind of good news. We're getting there, and I want to talk to you about the course and concerns you might have. And of course, I'll hang out here for a while to do some questions. I know people have been working on the Desmos for the quadratic, and I know there's some questions there. Hopefully, we can be able to work a little bit on that. All right, so why don't you friends go to the D2L, and in the D2L, there's the first announcement that you will see is an announcement that says Desmos Polygraph, and the link is right there, and then you just get on it. So let's take a look at the first one. This was a misunderstanding, I believe, on the part of the person who is responding, which is this person, Jacob Bernoulli. And because the first question is, well, let's look at the graph that this person chose, right? Look at it. It looks like it's a reciprocal of a linear, or the reciprocal of a linear over a linear, right? Like we did a little bit. Oh, here comes Suzanne. Anyway, so this is the graph that the person chose. And the first question was, does your graph have a corresponding parabola? The answer is no, which is correct. This is a reciprocal of a linear. Good. And then the next question is, does your graph touch more than 2 quadrants? And the answer was no. So let's read it. Does it touch more than 2 quadrants? It touches 1 here, 2 here, 3. It does touch more than 2 quadrants. So this person, I believe, said yes, maybe the way the question was worded, but it kind of misled the asker, and they chose the wrong one. Okay, so that's 1. And then the same thing happened to our same person. Now, another the guesser. So another reciprocal, this one is a bit tricky. Another reciprocal here is not linear, not quadratic. It's probably a reciprocal of a cubic. It's very quirky. So the person says no corresponding parabola, horizontal asymptote on the domain. Actually, this is an interesting way to ask the question. I'm going to speculate that the person means, does your graph have an asymptote on the x-axis? But I may be wrong, because horizontal asymptote in the domain, which you can see here. So I'm not sure how to interpret the question. The person said yes. By the way, I hope you realize sometimes you can say, I don't know. So I'm not sure because of the question or the answer were a bit tricky. It was hard to see. And then finally, success. Take a look at this one. A lot of you were successful on this graph or this graph. And they were, and this person is very methodical, always checking, is it a reciprocal of a parabola? touch more than 2 quadrants, positive and negative y values, and gradually eliminating. This is good questioning. Positive y values only. Well done. And there were a few others that were very, very good at asking questions. I'm going to pick just one more. Let's go here. The graph is this one, which is similar to the one we just saw. So there's the graph to n-defined point. I'm not sure I understand the question, but the answer, the person who was answering did understand it, which is better than I do. Do and find. If somebody can clarify it for me, that'd be great, because I don't get it. And then, but it was the right answer, I believe. And then, does the graph do more than 2 lines? Well, in a way, they all have 2 lines. The person said no. Yeah, that's interesting. This is a very interesting dialogue. Does it open going down? The person said yes, and this person was able to eliminate this. Okay, good. So some of the terminology that we might want to be looking at is what some of you have. Let's take a look at this. A lot of good questions here. Does the function touch more than 2 quadrants? Is this one? The answer is yes. Does the function have a vertical asymptote at x equals 0? And the answer is no. This is a very good dialogue. I'm impressed. Does the function have a horizontal asymptote at 0? No, it doesn't. Excellent, because if you look here, it goes underneath the x-axis, and then the vertical asymptote, the horizontal asymptote is further. Good. Does the function show a reciprocal? Yes, a reciprocal of a quadratic, right? It would be like this. The quadratic would be this way. Nice, 5 questions. Very good patience. Excellent. Thanks for playing. I hope you enjoyed. Sorry we can't debrief more, but I saw a lot of good stuff. I don't know if anybody has any comments, anything to add. And if you do, please do now. Please, don't be shy. Don't be shy. I hope, I mean, we throw in these because we've been playing with these functions, right? And it helps us see them in a little bit of a richer way. So thanks for playing. It's good. So now we're going to go and going to talk a little bit about what we did last class. And then we're going to go and do our little Jamboard. Okay. So this is, I'm going to highlight just a couple of things, and it's going to be quick. If there's somebody that needs me to go back, clarify something, I please beg you to say so. Malcolm and Andrew, I need to ask you to please keep an eye on the chat. And if somebody puts a question there because their microphone is off, then I will know. And you guys will let me know, please. Yes? Super. Thanks a lot. Okay, so we had this exercise last class. We have the graph of a rational function, which is the red, and we had the question of how do we determine all these characteristics. Whoops. Okay, the vertical asymptote. And graphically, we can see here, look at the graph and determine which point the graph doesn't touch on the on the y-axis, right? So we can see it here. The horizontal asymptote, we can virtually see with the end behaviors, right? How this is getting closer to 3 on this side and on that side, but it doesn't touch. And then the domain that is connected to the vertical asymptote, right? If the function does not exist, in this case we think it's -1, then the domain cannot be 1, right? Anything except for 1. And then the range connects to the horizontal asymptote, which in this case would be 3. And here the range would be anything but 3. Good. I like the way this team answered these 2 other questions, because I want you to think of these when we go to the Jamboard next. The x-intercept. How do we find the x-intercept? They did it, they told me here, actually physically, graphically, we can just see it, right? It's here, the x-intercept, and the y-intercept is here. So if we have it graphically, it's really a piece of cake. We can just figure it out. But they gave me the algebraic reasoning. They said, solve for x when y is 0 or f of x is 0. The x-intercept is, actually, I think these are a little reversed. Oops. When the x-intercept is here, and if I look at the coordinate of this point, it would be something like, let's say, 1/2, comma, 0. So the value of the function is 0. So that's correct. F of x is 0, and I figure out the x. So if I didn't have the graph, I take my equation, make f of x equals 0, and solve for x. And similarly, for the y-intercept, which is this point, I make x equals 0 on my function. If I had the equation, instead of putting x, I put 0 and figure the value of that, and that gives me the y-intercept. Good. Now the last, this is the ones that are kind of new. Okay, sorry about this. Positive and negative intervals. Positive intervals are when the function is above the x-axis. We can see it here, and we can see it here. So in our case, we talked about it. We would have, if we didn't have the graph, what would we do? Well, we look at where are the asymptotes, and we can put some values before the asymptotes and see what value they have. So if, in other words, if I substitute x negative 5 in my function, I'm interested in what sign it has. And then if I substitute x negative 2 and I realize that it's still positive, that means the function is positive there. And then I would look at other values, say, below the x-intercept, right? And that would give me the range for when the function is negative. Okay. And then the last part, okay, this is the trickiest one. The intervals of increase and decrease. I'll give you a hint. These functions always behave in the same way. And by that I mean, because this is a reciprocal of, well, not a reciprocal, excuse me. It's one linear divided by another linear function. They are always either increasing or decreasing. If it was a reciprocal of a quadratic, sometimes it increases and then decreases. The reciprocals of the quotient of two linears are always the same behavior, either always increasing or always decreasing. So that should be easy. But I like what this group said. Intervals are respective to the value of f of x or y or the range. In this graph, the function increases its interval as it comes near the vertical asymptote of negative 2. So we can see it's getting bigger. Same thing, you can put values. If you didn't have the graph, you put test values for this equation. You can test at negative 5, and then at negative 10, excuse me, and then at negative 5, and see if the values are getting bigger. And that's all you need to do, and that'll tell you that it's increasing. If the values, if say the value of negative 10 is smaller than the value of negative 5, the function is decreasing. Yeah, so you can use this. Okay, cool. So now we're gonna go and get our random groups. Excuse me for a second. And then now you can go to the first announcement in the D2L. And it's another Jamboard. Everybody, I hope, remembers how to work these things. You just go to the page for your group. And now this time, you don't have the graph. You have just the equation. And we're going to answer the questions that we answered last time that we just kind of went over graphically. But this time, imagine for a moment that you don't have a graph. You could sketch it if you wanted, but I want you to think of the algebraic part of it. Okay, so I'd let you go, and then we will see you in a little bit. I'm going to stop way back, but I need to stress it more. In some cases like this, I'm leaving the Jamboards there, and I think the Jamboards might be a good reference for you as kind of class notes. Having said that, when we do some of these debriefs, feel free to make notes, right? Use these as your note as we're talking, as we're debriefing. And other than that, they are there. Okay, cool. So I'm going to pick this group 11, because I think they did a very good job in their responses. So if you're not sure, come follow along, and hopefully these will help clarify some of the concepts, because they did a very good job. So one by one, how do we determine? Now this is our equation, right? And so that's it's two linear functions, one divided over the other. And so we find the vertical asymptote, set the denominator equal to 0, and solve for x. Pretty clear. So 3x plus 1 equals 0. If I were to solve that equation, I get that x equals -1/3, which is the equation of the vertical asymptote. So this is very much what we've been doing. This is really per se nothing different, but I like the way this team set it up. I'm gonna use red today, and so that's well explained and clear, and the answer is there. And the domain, well, these two are connected, aren't they? The domain x cannot be that -1/3. So I maybe should have done these together because really it's the same, they're connected. And now the horizontal asymptote and the range are also connected. And well, this is something, we didn't talk about degrees because we haven't done that, but I can see somebody already took this course before and they're familiar with this concept. What we did talk about last class was to look at the coefficients of the x. In other words, the 5 and the 3. And that ratio, because we were looking at the end behaviors, when x gets very, very, very big, and both the numerator and denominator, we can kind of discard the -2 and the 1, because we'll be multiplying 5 but infinity and 3 times infinity, which is a very strange idea. But if we were to do that, we would realize that we end up with 5/3. So that would be the horizontal asymptote, right? And this team elaborates if the degrees are different. In our case, we haven't talked about that. But if I had a quadratic divided by a linear, then I would look at the difference in the degrees. And in that case, it would be 1, and my asymptote would be maybe oblique, but we're not doing that here. So in this case, straight up, we do the quotient of these two, and that gives me the horizontal asymptote at 5/3. Pretty good job. And of course, that connects to the range, because the range, or the f of x, cannot be 5/3. Now, I'm going to share with you something that is very important. And it's going to sound like cheating, but I don't want you to think it like that. When you get questions like this, and you will later, and some of you might be getting it in calculus and stuff, nothing stops you from doing a little sketch, right? Because I mean, we're connecting the graphic and the visual, the graphic and the algebraic, but the visual is that link. So don't feel embarrassed or think you're cheating if you do a little sketch. That's fine. Some of you are doing grade 12 calculus, and a good chunk of that course has to do with curve sketching. So making those connections is important. So don't feel that you are cheating if you do a sketch, or if you even go to Desmos and graph it. The key idea is, let's say if you went to Desmos and graph this, then you need to explain to yourself algebraically how you could get there if you didn't have the graph. Good. Now let's do x and y intercepts. Very good, actually. They did a better job explaining than I'm doing at highlighting. So let's take a look here. The x and y intercepts. So this, of course, is one connection. solve for x when f of x is 0. So if I make these expressions 0, what I end up with is something like this. 5x minus 2 over 3x plus 1 equals 0. And don't think I'm that sneaky, but I actually did this in the last one here because I figure we may need it. And Zach's not here. Zach usually is a good spy. He didn't spy me that the answers kind of were here. I won't do it again, I promise, more or less. Okay, so this is what we talked about here. And this is what this team explained. I'm going to make this equation equal to 0. When the function is 0, we talked about this. That means the x-intercept, right? When f of x is 0. So basically what we're saying here is we have this equation 5x minus 2 divided by 3x plus 1. How do I solve this? Well, my first step would be just to take the denominator and multiply both sides by this denominator, right? So when I multiply on this side by 3x plus 1 and divide by 3x plus 1, that cancels. And when I multiply on this side 3x plus 1 times 0, it gives me 0. So this equation is equivalent to the one below it. And pardon my numbers, it's not easy to write with a mouse. So that becomes this equation. And then when I solve this equation, I get that x equals 2/5, which is the x-intercept. And I'm going to go back to team 11 and look at their answer for the y-intercept, right? And the y-intercept is now, we substitute when x is 0. So we would have 5 times 0 minus 2 divided by 3 times 0 plus 1, right? And then what value does that give us? And they found it at -2. So this would be -2 divided by 1 because it's become 0. So that's how we find the x-intercept. Excellent, excellent. Thank you, Team 11. I appreciate what you did. And then let's take a look at the next bit they did. The intervals where the function is positive or negative. Here, sub in values, x values above and below the x-intercept. How clever is that? Why is that? Because anything above the x-intercept is going to be positive. Anything below is going to be negative. Anything at the x-intercept, of course, is 0, and they're using, this team sees that and realizes that. So the only observation here is that these functions are a little tricky. So for example, here, what they did, we know that the x-intercept is at 2/5 or 0.4. So what they did was they're figuring out when the function is above 0.4, it is positive, and it's negative otherwise. Yes and no. This is a bit tricky because this function, when we graph it, it looks like this. Ish. Sorry, no, my asymptotes are not very good. It looks, I had it, it looks like this. Right, and we have the horizontal asymptote, the vertical asymptote, and we have here, somewhere here, the x-axis. And so this function has a y-intercept and an x-intercept. So there's a portion of this function somewhere here that is actually here when x is -0.4, but not always, because here, when I go to a negative value here, the function is above the x-axis. So let me see if I was able to explain this better in the last slide. Here. And I'm going to leave these, again, on the Jamboard. I'm going to delete the slides in between. So the last two slides will have a summary. So positive, negative, when f of x is 0, and this is very much what our team said, above the x-intercept, but keeping in mind the range given by the vertical asymptote. So in this case, our function is when x is less than 1/3, but also greater than 1/5. So let's take a look at this. Let's make sure that we see it. So I'm going to go to Desmos, 5x minus 2, 3x plus 1. Okay, so I hope you can see that the function is positive here and here. So what our team did very well was recognizing that above here, at that 0.4, the function is positive. That is true. And it is negative, but it's negative just here because at our asymptote, our vertical asymptote, we know that here is positive. And between the x-intercept and close to the vertical asymptote, the function is negative. So I wanted to check that. This part is tricky, so don't feel bad. I think you did fantastic because this is really tricky. So the negative interval then is when f of x is negative, meaning between the vertical asymptote and the x-intercept. So there's an interval there, negative 1/3 to 1/5, where the function is negative, right? I'm going to change the settings just for a moment. If I go from x being, say, -2 to +2, and then you can see here, there's a chunk of these that is negative, right? And our vertical asymptote, I think, was y equals -0.4, or no, I forgot. What was it? Okay. So actually, this is a trick in Desmos. Look at that. If I literally type 3x plus 1 equals 0, it figures out this line, which is the vertical asymptote, right? 1/3. So anything from 1/3 to here is negative. And how would we figure that if we didn't have the sketch? Well, we could do a little sketch, or we can do what our team did, take some values. But I would observe what happens before the asymptote, the vertical asymptote, and after, and then what happens after the x-intercept. Yeah, so this is tricky, but you did that very, very well, Team 11. And for that, you have our undying gratitude and respect. And then the intervals of decrease and increase, the last thing that they did, and let's just go back here. Choose x values approaching the x-intercept and vertical asymptotes from both sides to see if the values increase or decrease as they get closer. Awesome. So what I put here, and sorry about all these pages, was these functions. Actually, here are some ideas, right? Do a quick sketch and look at some test values in key intervals before the vertical asymptote, between, and after. And for intervals of increase and decrease, we have this situation, right? They're always either increasing or decreasing. So all I could do also is look at the signs of the leading coefficients, yes? In the numerator and the denominator. If this is positive, my function is going to be increasing. If this is negative, my function is going to be decreasing. In other words, if the signs of these two are the same, either both positive or both negative, my function increases. If one of them is negative, the function decreases. So that's kind of a shortcut for this. So there it is, kind of a deep analysis algebraically of what happens to determine all these things in this function. And I know it's a bit esoteric for many of you, and it's tricky. I just wanted to highlight these because I know these asymptotes and some other things you will use likely in calculus and other stuff. So, okay, so I'm going to go back here. Are there any questions? Let me pause. Malcolm or Andrew or Maya or Steve or Inolua, do you see any questions on the chat? No? Okay, sorry, that was a lot of talking. I apologize for that. So now I just want to talk about a couple of things very quickly, because I know that many of you are feeling a massive crunch about not only this course, but other courses. And I want to hopefully put your mind at ease. I want you to do your best within the circumstances that you have. In other words, there's a lot of flexibility. Some of you, and I have to tell you, I'm so impressed with you, send me notes saying, I'm going to be late for this assignment. I have circumstances. I'm putting due dates kind of to give you an idea of time that it might be reasonable for you to finish, but don't sweat it. Do not worry at all about, I'm not saying at all, do your best, right? But don't sweat the deadlines. I'd rather you take a little bit more time and produce better work than rush it and not understand it. We have 7 classes left.